All right, so what are we watching now? Finite Elements by the Atlas Computer Laboratory, publication date 1975. I don't really know what to think about this one. I've tried my hardest to not watch any of these at all, and this one included, I have no idea what we're getting into. It says engineering related, so that's all we're going on. Let's just learn about some finite elements, shall we?
The practical importance of a physical equation lies in its ability to predict.
These animations are like pretty sick already, like all the changing numbers and like motion and everything, so much more advanced animations than what we've seen in the past on this channel. So this, hands down, blowing everything out of the water. This is pretty good. I'm already having a good time. I don't even know what we're learning about and I'm already having fun.
The value of some unknown quantity. Unfortunately, not.
Dude, like there's movement in the animations. Like all of these other animations, maybe the camera has moved relative to them, but none of the actual graphics have moved themselves. I know I didn't even expect to be going off like this on animation 5 seconds in, but I'm just so glad. I'm so happy to be seeing animations like this.
All physical equations are so simple. Frequently, we find situations.
Dude, like this transformation, like how did any of this even happen? Like I don't, like these blow my mind even more so than like most of the photography I watch. Like how did somebody animate this on film back in the day? Like where did this equation even come from? Like it came from the one turned into this whole equation, and then this x turned into the other parentheses, and then the 5 turned into an x, and then this little 5-pound weight turned into like this. Just if you watch all this animation, somebody has to appreciate it, right? Like I appreciate this because partially what I do is animation, not really similar to what we're seeing on screen, but a form of animation nonetheless. But this is really just amazing. Already I'm impressed. We're not even like a second into this and I've just interrupted so many times already. Let's just keep going and keep in mind that these are some cool animations.
The finite element method is one technique for overcoming this problem.
Dude, this title screen is so dim, I could barely even recognize that these were letters. So Finite Elements, that's the title. This is already so sick. I hope there's credits and I hope we get to see the computer graphics credits because whoever got these deserves a prize. And you know what? This is such a good font. It's all so good. It's so, oh man, I'm having a good time.
An engineer designing a bridge.
Dude, these animations, is this all gonna be animated? See, that's the thing, is most of what I watch is just like boring black and white footage that like barely even feels like it's moving. But this is like awesome. This kind of looks like a child's drawing, but the fact that it's all animated makes it so cool.
We'll need to know how the proposed structure will behave under load. The equation describing the distribution of structural stresses are...
Dude, we just got another glip. I just did not understand what we're talking about at all because we lost something there, but we'll just keep rolling through it.
...known, but they can't be directly solved for a complicated...
Oh, look at this. Now the bridge is moving. See, usually in old animation, you can tell which things are going to move and which things are going to stay put based on which parts are the background paintings and which parts are actually hand-cell drawn, like ink and whatever, ink cell. But here, I couldn't tell that this was going to move separate from the background at all. This is still like really, really good animation.
...shape such as a bridge.
Dude, it's moving in 3 dimensions. Obviously, they're faking it a little, but like they have 3-dimensional motion in this. When is this even from? 1975? That's not too long ago, but I'm being blown away every second by this.
However, the equations can be solved for very simple...
Oh man, of course they have the most impressive animations, but their audio keeps cutting out, so I can't actually understand what they're saying. They have such good visuals, but their audio is just trash.
Finite element method takes advantage.
Yeah, we keep cutting both in time and in audio, which is, I hope we don't do that this whole time, but I have lost some information. I just want to give myself that excuse for later too.
It's the single complicated shape with an approximately equivalent network of simple elements. The overall pattern of elements is referred to as...
Dude, a freaking real engineering level animations right now. This is great. I know I've talked about nothing but the animations, but that's really, that's really what we're excelling at here.
The finite element mesh. And this pattern will be unique to each new problem. The initial step is to design this mesh. And for this, we must first
Yeah, I'm already like completely lost. Like, what are we doing with mesh all of a sudden? Like, I'm blaming the audio cuts. Like, I lost my train of thought, but I don't think that's my fault.
decide what kind of elements we'll use. One-dimensional rods,
Dude, see, there's so many different layers of this animation, right? Like those lines had to be animated, but then the whole animation had to move itself as well, which is just like, oh, that's two layers instead of one. People don't appreciate the complexity on display on screen right now.
or two-dimensional triangles, or quadrilaterals. Or three-dimensional blocks, or a combination of different kinds of elements.
Yeah, like how'd they transition all these blocks in? Like what method are they doing this? They're editing it on film somehow. It might just be like hand drawn or something, which would, yeah, that probably would make sense. It might just all be hand drawn, but these are still complicated. Even if these are hand drawn, that actually makes it more impressive, doesn't it?
The accuracy of the calculation is going to depend on the number of elements we choose to have in the mesh.
Still, though, I don't know what we're talking about. I thought we were talking about like elements as in the periodic table. Clearly, we're talking about something different, but there's a lot of colors now, and I am lost. But I'll try to pay more attention.
The more elements we have, the smaller each one will be, and the more accurate the results.
Oh, we're talking about computer animation, I think. Oh, that would be so fitting if this is about like elements on a computer which is allowing them to have all these animations. That would be beautiful if that's actually the case. I really thought this was going to be about like the periodic table, not computer animation. So we'll see. We'll see what this actually is about.
Unfortunately, more elements also means more calculations to be done. For reasons of economy, therefore, we look for the happy medium. Just enough elements to give adequate accuracy.
Yeah, this is like intro to computer animation, like how to build an object in 3D, make it consist of like polygons and whatnot. This is what they should be watching on like Corridor Crew, not this.
Within a reasonable computing time. In our example of the bridge, we've chosen to use elements defined by 8 points. These points are referred to as nodes.
All right, these are defined by 8 points. Each one is a node. Yeah, we're totally into like computer graphics at this point.
In general, we regard each node as being capable of moving both horizontally and vertically.
Dude, this is actually so funny because this is like actual animation. I know that sounds really silly and obvious to say, but like this is such a good insight. Oh my gosh, I'm so glad I picked this. I really am in for a surprise on this one.
The exception will be those points around the outside edge that we can regard as immovably fixed. These boundary conditions must be included to complete the description of the physical problem so that the solution will be uniquely defined. Finally, we must spend...
Yeah, this is probably like the very first time we were able to do like computer graphic manipulations like this. Like this probably, like I said, this had to be hand drawn, around this time. I guess this is one of the first demonstrations of computers doing it though. This is so sick.
Specify the elastic properties of the material and what...
I'm glad that this underscores why I was so shocked by the animations in the very beginning of this, because this whole thing is about animation and new techniques in animation that's why I was surprised in all the new techniques in animation I was seeing on screen. It's a coming full circle now.
Loading we wish to apply. In this example, we've chosen a large point load at the center of the bridge. The mathematical treatment aims at deriving an equation describing the whole system. We start from...
Dude, this is a groovy little graphic right here. See, this is what's so good is all these little graphics, all these little colors. It's all so good. Like the color choice, all of it. The graphic design, it's phenomenal.
From a basic relationship expressing the displacement of any node as a function...
Dude, whoa, the graphic. Oh, see, like, yeah, even the effects on the text. See, oh man, such good work.
Function of the node's coordinates.
Again, that looks like a PowerPoint, like, preset graphic, but to have been doing this on computers back in the day is really impressive.
X and Y. In this example...
Dude, yeah, you lost me once you started bringing in all these letters and things.
The elements have 8 nodes, and for each of these, we write an equation describing the displacement of the node as a function of its coordinates. This gives us 8 equations for the whole element,
Yeah, I really hope you guys are taking notes, by the way. There will be a test at the end of this.
which together form a matrix. This matrix is now the starting point for a series of steps based on the fundamental laws of mechanics.
I don't want anyone to feel bad if they are not following along. You are in good company, is all I have to say.
Step 1 relates displacements to stresses. From stresses, we obtain strain energy.
I don't know what's going on, but again, I like the graphical design aspect of all of this. The color choice, all the imagery, all the changes that's going on screen. Very engaging. I'm definitely engaged.
And from this, we derive potential energy. And finally, from minimum potential energy, we obtain a pair of system equations for the complete element. By analogy with the equation of a simple spring, this new matrix is called the stiffness matrix for the element.
I don't think this was being shown to kids in high school. Maybe back in the 70s, high school was different, but I don't know if this was for... This might have been like a college course or something. Where did this come from? Who made this? Atlas Computer Laboratory? Who knows where this came from, to be honest? I don't even think we got an answer on that.
Instead of a single displacement x, the matrix operates on the vector x, whose components are the displacements for the whole element. We carry out this process for every element in the mesh.
These are like 3D animations, like basic 3D, but the whole perspective of the square is like shifting. It's people don't understand how complex this is.
So that we now have a stiffness matrix for each one. The important step now is to combine all these individual matrices into a single large matrix representing the stiffness
Dude, what, yeah, these animations, the bounce and everything, I don't know how they did this, to be honest, but it is very impressive. I gotta stop interrupting just to compliment the animations, but it really is. Like, every single different thing they do is a different, example of their capabilities.
of the whole system.
Like, look at that bounce. Like, how'd they get the whole layer to deform like that? It's just, I don't know. It's impressive. It's game gotta respect game, I guess, at the end of the day.
Now, any two neighboring elements will have nodes in common. So values for common nodes will appear in both matrices. The matrices can therefore be combined by a simple merging technique. In practice, the process of solving the overall system equation is done concurrently with the combining of the matrices.
Dude, I don't know if all those colors matched, though. I really don't know, the metaphorical understanding of these colors at this point. I am kind of lost in the metaphor.
The whole process is known as reduction. We now use a standard procedure to eliminate part of the matrix. The rows of the matrix represent a set of simultaneous equations. We solve the first equation and substitute the solution in the remaining ones, repeating until finally we're ready to add on the matrix for the next element.
But what is even happening, though? Am I, the only one who is just completely lost now? Is this making sense to anyone?
Eventually, when the last matrix has been added, we're left with the solution for a single node. We can now use this result rather like a key, working backwards through all the equations of the system until at last the displacement of every node is obtained. From these results, we can quickly calculate the corresponding stresses. In this example, we're showing the stresses as a contour diagram, with the areas of greatest compression shown in red and greatest tension in dark blue.
All right, so they're simulating the stresses, the internal stresses that will be experienced by a bridge of this shape, and they're looking for where experiences the greatest pressure, I guess. But I don't really know how the nodes was all connected to that. Maybe somebody in the comments can enlighten me, but I kind of feel like I missed out on a part of that explanation there.
The process we've been watching requires vast numbers of individual calculations to be done, and for this reason can only be done on the computer. Furthermore, the calculations usually involve such large matrices that a powerful computer with a large core store is needed. A great advantage of the computer, however, is that now we've completed the calculation for a load at one point, it's a very simple matter to repeat the whole thing with the load moved to another point. If we keep
It's funny how they're like just starting to discover like how useful computers are. Like, oh wow, we can like have it calculate all these points for us like it's almost instantly. Probably not for them almost instantly. It probably took a while for them to calculate these even on a computer, but even still it must have felt like they were tearing through them compared to doing it by hand. So, it's funny to hear the admiration for computers that they had all the way back then.
repeating the process with a sequence of different points, we can eventually build up a continuous animated sequence showing the behavior of the bridge as the load moves across it.
So was this not about animation? Was I just talking about animation for no reason then? Like this is very impressive for no reason then.
This particular sequence was calculated using the PAFEC Finite Elements computer program.
Dude, like look at all these shape layers that are changing and shifting. Like I I have no idea how they did this. Like this is so impressive. Like look at all the every single shape, like every single color is a different shape layer somehow. That's how, that's the terminology that would exist on like After Effects. I don't know exactly what this would have been. It might be like real practical or something. I don't know. No, it's all calculated on computers. I don't know how they're making this. Like it's impressive enough animation that I just don't know what's going on.
Developed in the mechanical engineering department at Nottingham University, and was then drawn onto film using the Antics graphic animation program at the Atlas Computer Laboratory.
So this was all drawn onto film using a special technique.
Drawn onto film using the Antics graphic animation program.
Antics graphic animation program.
The Atlas Computer Laboratory.
At the Atlas Computer Laboratory. So interesting. So that's why we saw the name Atlas Computer Laboratory. So all of these animations were made by a very special computer, I guess, at some sort of laboratory. I knew there was a reason all these animations were very impressive.
Many other users of the Atlas Laboratory have also been working on applications of the finite element method. The Civil Engineering Department at Southampton University is developing a computer program to study the behavior of fluids in motion. When fully developed, this program could find important practical applications in the design of offshore structures.
Oh wow, so this is like the very first like fluid simulations almost. So they're trying to calculate like how fluid moves through like an area. This is just so fascinating. This is like the very earliest days of computer calculations, I guess. And it's funny to see what sort of things we were trying to solve using computers. Like anything that needed a massive amount of data input, we were immediately giving to the computers. I guess we're no different today. I also really like this color purple. Like what a strange color. I don't know. I don't know if that's good commentary or not, but it's like this is just it's a nice lavender. It's not the typical color you get for like a physics explanation.
Such as North Sea oil rigs. In this example, we're simulating a channel containing a rectangular block obstruction. The finite element mesh is based on triangular elements. We introduce a steady flow of liquid into the channel. The speed of flow, the viscosity of the liquid, and the dimensions of the channel are all specified. The upper diagram shows the path of the fluid. The distribution.
Wow, this is really interesting. This is like the very first like form of animation of like I don't even know what it's called, like I guess like theoretical physics, like I don't know, simulation almost. Like that's kind of what we're seeing here. It's like it's calculating the different like trajectories of things. I don't know. This is very impressive.
The distribution of free streamlines. The lower diagram shows what are called stationary streamlines. It contains the same information as the upper diagram, except that the uniform velocity of unobstructed steady flow has been subtracted in such a way as to exaggerate and clarify the small variations we wish to study.
That was a pretty non-specific answer. Like, it kind of just sounds like they just made it up based on what they saw.
At this point, we've made a change in the conditions, equivalent to speeding up the flow. The streamlines change until again they form a steady state. Increasing the speed of flow still further, however, and a steady state is no longer possible. Vortices begin to form.
Dude, this is so funny. This is like what Smarter Every Day has made videos about. Like I've seen slow motion footage of this happening now. It's just so amazing to see like the physics simulations of this from what 1970s. Like this really is like a very ahead of its time glimpse into science.
and eventually a dynamic equilibrium state is
Like
reached.
it's so funny seeing these lines go and try to imitate the flow of air because they're not moving like air. Like they're imitating it obviously, but they're not like perfectly illustrating it, which we've only since been able to figure out based on like high-speed cameras and whatnot.
Finally, one more example, also from Southampton. This program
Is this Hong Kong or Macau or something? This map looks familiar. Is this? It looks like, oh, is it Hong Kong? What is it? Yeah, I don't know. I think that's what it is. Maybe Macau, but this looks like one of those like Chinese city-states. I could be wrong, but that's just what this map is reminding me of.
This program is designed to study the dispersion of pollutants deposited in tidal waters. The finite element mesh here corresponds to the eastern Solent extending to Portsmouth, and the thickness of the elements corresponds to the depth of the water.
Portsmouth, so this is probably England somewhere, not China. That makes a lot more sense.
We also include the rise and fall of the tide.
Dude, the freaking tide animation, I love it. Oh my gosh, like the text alone, this looks like the original like Dune text, doesn't it? And then the animation inside of it with the white going up to illustrate the tide going down. Oh, so good. Such good. That's such a creative little choice, you know? That's what it was. Like how, you know, somebody asked the director like how do we illustrate the tide going up and down using the text tide? And they were like, "Oh, just make the white, you know, it's such an artistic choice."
Tide and insert a specified outfall of pollutants. The computer program then shows us clearly whether the pollutants will be carried straight out to sea or whether tidal effects will cause dangerous concentrations to build up near the beaches.
Dude, I wonder if these predictions were like any way accurate because based on the animations, even though the animations are good, they don't seem like 100%, you know, scientifically real. Like I don't know if that's actually how a pollutant would disperse in water, you know. I think it's a lot more complex than that.
Once again, from this example we could now continue.
Like this looks like almost hand animated. I don't know. It might not be. This all might be scientific data that they're just plugging into some animation computer, but it looks imperfect, I guess, is what I'm saying.
The same program may be used for any other area of water and any specified discharge of pollutants. We can investigate varying the rate of discharge and timing it to fit in with the movement of the tide. We can take into account the biological...
I like how that's the application that they use. Not to like stop the pollution, but just when to time it better with the tides. You know, like, oh, when everything works out, we'll still be polluting just as much, but we'll do it in a better way. Like, oh, great.
decay of the pollutant. And we can also include the background level of pollution from the rivers themselves.
This must have been so exciting to see computers calculate stuff like that. Like, that's not that impressive to me now, but like to see all of that data must have been so exciting. The world must have been so open to you back then when you could just like calculate anything you wanted. I guess you can still do that, obviously, but it's less impressive now. This is like the cutting edge of computer calculation and graphics.
A major advantage of the finite element method is the ability to work with arbitrary shapes. This overcomes many of the limitations of older numerical techniques and gives the method a flexibility comparable to the use of physical models, but without their limitations.
See, that's interesting. So people haven't really been able to calculate loads or stresses or whatever on like irregular shapes. They've only been able to mathematically do it on squares or circles or things that have like mathematical laws or easy to understand mathematical laws. But something like a bridge obviously is a bit harder to understand from a shapes and like stresses perspective. So a computer really does excel at that point. And again, something that would have been so unthinkable or unfathomable to a person to calculate, but for a computer to do is not that hard. It must have been so cool to see this for the first time.
For example, different materials can be investigated easily by specifying different material properties as program data, properties that are difficult to vary in physical models. We can simulate life-size structures on the computer, whereas with the use of small-scale models, we're left with the scaling up problems. Engineering research today is becoming...
That's funny how they were aware of the resolution issues, I guess, with these simulations. Like, they obviously weren't perfect, and it's good that they admitted that. Obviously, I've been pointing that out, but that's an aspect of conducting scientific research like this, is to be aware that this is not like a perfect calculation of real life.
Increasingly sophisticated. It's often only by using the largest and fastest computers that we can hope to solve the complicated systems of equations representing a complex physical situation. With modern powerful computers, it's also possible to conduct a comprehensive parameter search using a finite element program for large numbers of different cases in order to optimize the system. The finite element method can be applied to the widest possible variety of engineering. Undoubtedly, it can be said to lead the field in modern engineering computing methods.
Dude, even the graphics for the end were crazy. No way. Oh, look at this. Oh my gosh. Yeah. Oh, this is so sick. These are the craziest credits we'll see for any program ever. Like, look at this. You don't even see these sorts of credits nowadays in film. Like the endless zoom in too, like that effect. Oh my gosh, so good, so impressive. Animation and music by the Antix computer system. Interesting. So shout out to the Antix computer system. Whatever that was, it was a step above what they had before. On an ICL 1906A computer. That's so funny how they like put in the credits like what computer they used for all this. Like, I guess that's fair. The computer did a lot of the work. It might as well earn a spot in the credits. That's so funny. It's just, yeah, it's just funny. I don't know that they put the computer in the credits. You know, like good for it. I don't know. How many instances are there in human history of computers being given a credit in like an artistic work? I mean, this might not be considered an artistic work, but it still has credits and there's a computer in it. So I feel like that was like the first thing I've ever watched on this channel where I don't actually understand what I just saw. I know I watched 12 minutes of Finite Elements, but I couldn't write 12 words on what Finite Elements actually means. Can I do this? Can I come up with an adequate summary for what I just watched? So from what I understand, Finite Elements were like the basic building blocks of like graphical computation. I don't know if that makes any sense, but like every single little finite element, I guess, is something that a computer calculates and altogether with all the other finite elements comes to some sort of conclusion or some sort of answer that it uses to fill in, you know, something graphical or colorful or something like that. That's just my take on it. I don't know if those have anything to do with the quality of animations that we just watched. It feels like it does because it was all computer animated, but I don't know. Like it's about simulating things on a computer and then all of the animations were amazing. I just can't figure it out. I can't figure out if the animations are good just because like they're good or if the subject of Finite Elements demanded such good animations because it was so valuable to the field of animation. I think it might just be the first one. I think this might just be some really cool early footage. This is so cool. Just looking, I'm scrolling through the timeline and just looking at all the animations like in fast speed, and they actually look a lot better. I think even though I don't quite understand Finite Elements, maybe that just means I need to learn more about them. I guess this was related to graphics and animation, but it also wasn't. I can't tell. I can't tell how much of this was just really great, fantastic animation and how much of it was pertinent animation that was informed by like the subject material, I guess. So I'm just going to say I'm really impressed with what I saw today. I don't know if it taught me exactly what it intended to, but I definitely had fun watching. And I think that's kind of the point of Finite Elements, is to create a good watching experience for data. So, you know, I can't argue with that. So all that I have left to say is thanks for watching, and if you would like to support what I do here, go and donate to the Internet Archive. Not to me, but to the Internet Archive. That's where I get all this from, so give them all your love, not me. Thank you. Let's just cut to black.